So hello everyone, my name is Zikuan Huang, and I'm a student, incoming PhD student at Cambridge University, but I'm currently a researcher at Shanghai Qizhi Institute. And this work was done when I was at Tsinghua University. Two co-authors are both from UCSD. They are Zihan Hao and Qipeng Liu. So this paper is accepted by Stock 2026. And now let's start it. So let's start from a famous question, collision finding. Let's say you have a random function h. For the domain is like a full domain, and the image is a lambda bit image. And the task is to find two elements from the domain such that they are equal. For classical algorithm, we all know that the best classical algorithm runs in time square root of the size of the image. And it's famous because it's a birthday paradox. And for quantum algorithm, there's a famous algorithm called BHT algorithm, which achieves, I mean, it's a time-space tradeoff, but if you optimize in terms of time, it gives you 2 to the lambda divided by 3, a number of queries to h. And this is relevant to, so this is a quantum advantage, but it's not a exponential advantage. It's only a polynomial advantage if you think of the size of the image as a polynomial. And this advantage is important because it actually affects the parameter of crypto hash functions. So to remind you guys about classical algorithms that solve this collision finding problem, let's start with a very interesting algorithm called the polar row algorithm. If you guys don't know this, it's very worth you guys to study this. So this is a very elegant classical algorithm that only uses I would say constant space. By saying constant, I mean like constant number of input-output pairs. That solves this collision finding problem. And this algorithm also achieves the best time complexity. By the way, when I say time complexity in this talk, what I mean is basically a query complexity, queries to this hash function h. And this polar row algorithm achieves constant space and optimal query complexity. But when we try to achieve the optimal time complexity in the quantum case, we actually need a very big space. So for BHT algorithm, we need 2 to the lambda divided by 3 time and 2 to the lambda divided by 3 space. So we don't know whether this is like optimal or not. And we will see this in the next page that this is a very interesting open problem. And basically this BHT algorithm is a Grover search. So it first prepare a table, input-output pair table that stores 2 to the lambda divided by 3 input-output pairs, and then it runs a Grover search on X such that h of X appears in this table. So for each random h of X, the probability that it appears in this table is roughly this 2 to the lambda divided by 2 to the 2 lambda divided by 3. So the complexity of this Grover search is this one. So this is the BHT algorithm. So why is this bad? Because actually quantum space is much more expensive. Like we can tolerate, we can run the algorithm for long enough time to find a collision, but we don't really have this much space. So especially for quantum memory, because importantly, if you want to run this on a real quantum computer, each quantum memory, each qubit is like a thousands or hundreds of physical qubits. So it's very expensive to use quantum memory. And this is not realistic because it's exponential amount of space. So it doesn't really, it's not like time, because for time you can run it for long enough. So natural question, which I mentioned in the last page, is that is this exponential space really required? So that is to ask, let's say if S is polynomial, then can we still achieve this best Curie complexity? So this is one of the 10 open problems related to quantum Curie complexity presented by Scott Aronson. That is, well, the original statement is a bit different, but essentially it says whether this memory is needed, whether there's a exponential space lower bound for optimal collision finding. So now let's review the landscape of this problem. We here have a birthday paradox algorithm which takes square root. Oh, by the way, here this capital N means the size of the domain. Sorry, the size of the image. And this birthday paradox is, well, you guys all know it's square root. And we have this polar row algorithm, which use square root query complexity and constant space complexity. I add a tilde here, so there might be some like log factors, but we can ignore them. And all of these are like all the classical algorithms lies above this line. And we also have this BHT algorithm. It is actually a trade-off, but we are able to achieve the best query complexity at n to the 1/3, which also we need to also use a large amount of memory to achieve this. And we also know that this line, proved by a very famous work, that says basically if you want to solve collision finding, then the best quantum algorithm is above this line. So the conjecture is whether this is the real part of all quantum algorithms. So are there any, oh, by the way, below this, it's always impossible because we have this lower bound. So the open question is this part. Do we actually know that there's algorithm in this part, or can we show that all the algorithm must lie above this curve? Okay, so this is like the landscape of this collision finding problem. So in general, the difficulty of answering this question is that current results for space-time trade-offs are all not for short output, are not, I would say, they are, some of them are for short outputs, but they are not in the random oracle model. If it's a search problem in the random oracle model, then all of these space-time trade-off are for long output problem. I will later on explain what is long output problem. So, and also this is even challenging in the classical setting. So for what is a long output problem? Long output problem is basically a problem that the output length is larger than the space you need to compute it. So what does this mean? Because how do you actually compute a problem that its output is larger than your space? Well, in general, the model would be that you actually have a additional tape, like an additional write-only tape that you can write your answer to that tape, and that tape is write-only. Like you cannot read from it, and you cannot like edit it. It's only like a write-only. Like once you write something on that tape, then it's done. Like you just print the answer. And we also have like an internal working space that is smaller than the output. So for this type of problem, like for this type of Oracle search problem, the generic model would be that time complexity is like the number of queries, and the space is we will only count the working memory as space. So what an algorithm can do in this model is basically it can perform local computation on a bounded memory. It can, so the second point is very important. It can actually discard bits. For quantum algorithm here is like a discard qubits. You can trace out quantum systems, and you can also introduce new bits that is initialized as 0, as long as for every time, like for every step, the memory that you hold does not exist the memory limit. It's okay. So there are some non-generic model. Something worth notice is that in streaming model, we actually do have a very famous result by Ron Raz, a streaming space-time trade-off. And there are also some results in the pebbling model. But these are not considered today because today we're only considering this Oracle search problem. And previously in the generic model, we have either a long output result, which means that the output is larger than your space, or we have a weak trade-off. And the question of whether there is a short output problem that satisfies space-time trade-off is still open. And yeah, so this we will actually resolve this problem. In this work, we are presenting the first space-time trade-off for short output problem. So before we talk about our result, we want to show like how do we prove long output result previously. There are some very famous paper regarding this type of long output problems. One of them is to find k distinct collision pairs under Oracle H. So here you can imagine that this k is something like n to the 0.1, or I mean at least here by saying n, I mean like the size of the image, like n to the 0.1 is actually exponential. So this is an example for long output problems. And previous results show that for classical algorithm, we have this type of strong space-time trade-off. And for quantum algorithm, we also have a similar one. So this T means the number of queries. This S means the size of your working memory. And let's look at. So basically, the idea of the proof is to use progress measure, and now we will introduce this progress measure technique. So to do progress measure, we have to first divide the algorithm into several parts. This is what we call slicing technique. So let's view the algorithm as this rectangle in time and memory diagram, and we want to slice this algorithm into different parts. Like here we have a different part of the algorithm, and each part of the algorithm will output some collision pairs. So you can imagine there's a write-only tape on the sky, and each part of the algorithm print some collisions to that tape. So let's say that there are L slices. And by pigeonhole principle, we know that there should be at least one block or one slice that in that block there are more than k divided by L collision pairs output. And so let's say that there's now we want to view like each block as a sub-algorithm. And this algorithm takes, well, it uses T divided by L queries, and it receives a S-bit advice or S-qubit advice. So what is this advice? This advice is like the working memory carry on from its previous part. Like, for example, for the I slice, it actually receives the working memory passed on from its previous slice. And we assume that there are no space constraints inside each slice. So this is a relaxation of the problem, so it actually gives a stronger bound. And how do we deal with this S-bit advice? Is to just guess it. So we don't know what is it, but we, instead of using the advice, we use a random string, or in the quantum case, we use maximally mixed state. So by changing this advice to a mixed state, we actually get a 2 to the s factor. Actually, it's a 2 to the minus s decay on the success probability. So to prove the lower bound, we want to show that there must be one block such that that block without advice or with a mixed maximally mixed advice is able to produce k divided by l, more than k divided by l pairs with probability oh, by the way, this might be a typo. It's like a p times 2 to the minus s. So, oh, sorry. This is not a typo, sorry. So this means that if we want to prove the final result, how do we derive the final result? It's by proving each slice, like for each slice, if we can prove that within that slice, the probability of outputting k divided by all pairs is at most 2 to the s times p, then the overall success probability is L times 2 to the s times p. So this is like a union bound type of argument. So now we reduce a space-time trade-off problem to a time bound, like a time bound problem. Like we don't care about space anymore because we guessed the result. We guessed the advice in each part. So we get rid of space, and we are only interested in the relation between the number of query you use and the probability that you produce k divided by L pairs. So one may notice that this slicing technique doesn't really work for short output problems because in short output problems we don't really have a progress. We either get the answer or we don't. We don't really have a measure on like how many distinct collision pairs we get. So this slicing technique doesn't really work in the short output setting. So before introducing how do we incorporate this short output setting, let me first introduce a tool called the compressor oracle. For someone that is not familiar with quantum, you can just think of this as, let's say, a lazy sample technique for random oracle. So the compressed oracle is a way to actually record the amount of information that you get when you query a quantum random oracle. So let's say the random oracle is initialized to the state here. You have a x, which is x and u are query register, and w is the working register. You also have a superposition quantum oracle. So this sigma on h is among all all random oracles, and they are in a uniform superposition. So for standard oracle access is this type of gate. Like you actually add the oracle output to U. By conjugating this gate with hardware gates, you actually get the face oracle. So for in the face oracle, the query is done in this way. Like in the second line, you add the face. This face depends on the inner product of h of x and u. So this is the face oracle. And Mark's work tells us that this face oracle, like this face, is actually a global face, and it's you can think of it as a face acting on the working register, or you can also think of it as a face that acts on the oracle register. So basically, you can move this face to the oracle register, and what you get here is that for each quantum query to the oracle, the query does not quote in fact affect the working register, but it affects the oracle register. So if you view the oracle register in the Fourier basis or in the hardware basis in the setting of inner product, what you get is what we call a hardware oracle. Oh, by the way, I use this Fourier oracle because this is like a F2 Fourier oracle. In this oracle, each time when you query the oracle, you are actually writing U on the x position. You are XORing this U on the x position. So the compressed oracle is like, well, there's a decomposition process that decompose a bot, which is a notation for not knowing anything on that like bot on the x position means that the algorithm doesn't really know anything on x on h of x. It decomposes this bot to a uniform superposition, and it also it remains the same for other bases. Okay, so to recap what we are doing in the oracle recording, we're using this lemma from a previous work that, well, you don't actually need to care about the details, but it's like basically the oracle recording works as follows. So initially you have a all bot database. In the classical setting, this means that the oracle is not sampled yet, and here it's like it's all superposition, and the algorithm does not know anything about the oracle. And for each oracle query, after each oracle query, we want to measure like what is the progress of the algorithm. So we define this pi k being that being a projector onto all the database such that there are at least k distinct collisions in the database. Here we don't really count the bot symbol because it's like a not sampled yet symbol in the database. And to measure the progress, we use, let's say, delta tk being the amplitude of the state in this in pi k after t queries. So in the classical case, you can think of this as the probability of finding well, in quantum case, it's not probability, but in the classical case, you can think of this as the probability of finding k distinct collisions after you query the oracle t times. And so normally what you have is a this type of recursion recursion. So this basically means once a new oracle, once you query the oracle on new point, you either get 0 new collisions, which is which you have the amplitude from delta t minus 1k, and you had a new collision, which the amplitude is basically OT divided by N, because the size of the database is at most T, and you get this term. So this is basically the normal way of proving progress of the algorithm. And finally, we want to bound delta capital T star and capital K star, which is like T star and K star are the number of query and the target. Okay. So after introducing this slicing technique and oracle recording technique, we ask the following questions, because from previous pages, you guys know that it's very hard to come up with this slicing argument if the problem is a short output problems. So our question is that, can we actually establish a space-time trade-off for a problem with short outputs? So this actually, in other words, to achieve, let's say, to achieve a quantum algorithm, optimal quantum algorithm, do we need exponential space?
Sorry, could I interrupt you and for a small clarification? Yeah. So I think at some point you mentioned that because the output is short, it is hard to come up with a progress measure. Mm-hmm. Could you explain that a bit? I didn't fully grasp how you what the difficulty is. Yeah, I think at some point you mentioned it and I nodded along, but it would be nice if you explain it.
So basically, the progress measure, like the slicing technique here, is to say that we divide the algorithm into several parts, and we said let's calculate how many collisions each part contributes.
Right.
So if there are, let's say, k collisions in total, then there must be a block or a slice that contributes more than, or at least k divided by L pairs. But now let's replace this number of collision to, let's say, one collision. We want to say that we want to study the problem of space-time trade-off for finding one collision. Then we can't really do the same thing, because we can say that we can't say that like there must be a block that outputs 1 over L collision, which is not even an integer. I mean, that is not possible. Like, you cannot count that.
Do I follow up on another question?
Oh, yeah.
So even in the k distinct collision finding problem, like, what if the number of slices? So the number of slices is upon us, right? Like, it depends algorithm to algorithm. So if I can break the algorithm.
Well, the number, like this L is a parameter, right, that is set in the proof. Like, we in the proof we adjust this L so that we can prove the lower bounds. It's not like naturally there's an L. Naturally there's no L, and in the proof we adjust what is this L to make our bound stronger.
Wait, so we are trying to argue that there does not exist an algorithm which can be broken into L slices, which can solve the k distinctness problem.
Mm-hmm.
So is that how the proof works? Like, sorry, like my concern was, if L is larger than k, then we wouldn't have a valid progress measure in that case as well, right?
Oh, so in the proof we actually set this L to be equal to some sort of let me write it. Like, in the proof we actually set L equal to, I think it's something like k to the some alpha n to the beta, like for some alpha beta. Like, we set L equals to this and we do the proof. So this is like a parameter that we try to adjust in the to make the lower bound meaningful.
Okay.
Yeah.
Yeah. Maybe I'll like figure it out in a bit.
Yeah. I mean, you can think of this like, what if we take this to the extreme? Let's say L equal to 1. If L equal to 1, then there's really no space constraint, because between, like, inside a block, there's no space constraint.
Each slice there is no space constraint, right?
Yeah, there's no constraint inside a block. So if you take L equal to 1, you cannot get any meaningful bound, because there's no space constraint. Let's say you take L equal to K. Then in this case, the problem is that for each block, the requirement is too weak, because the requirement is that in each block you want to find at
least one pair.
At least one pair with, let's say, some number of queries. This is too weak to prove the general statement. So we want to set this out so that it is good enough that we can get a meaningful bound. Okay, do I answer your question?
Yeah.
Okay.
Thank you.
Okay. Yeah. So we answer both questions affirmatively. This is not the original question from Scott Aronson, because Scott asked whether this space-time trade-off exists for collision finding this problem on its own. But our result is that we construct a problem that satisfies this space-time trade-off, and this problem is short outputs. So this actually serves a very important step towards answering Scott's question. So let's look back at this compressed oracle technique. One thing we have noticed from this is, like, this is a very important observation, is that, well, there's a oracle duality where querying an oracle is in fact writing on the hardware basis of the oracle. So these two are the same. So basically it means that a oracle on its own is also a write-only register. Or you can say an oracle on its own is a write-only tape. So what's the application of this observation? Let's look back at the slicing technique. So in the slicing technique, we measure the progress here using the number of collisions. So if, well, in the model, all these collisions are written on a write-only tape. So by the oracle duality, a write-only tape is a oracle. So now what if we switch this write-only tape into a oracle G? Okay. So let's say we want to search a pair of X and X prime such that it forms a collision in H, which is the original oracle. And this tuple satisfies some constraint with respect to G. Let's say it satisfies G X prime equal to 0, where G is an oracle, let's say it takes input 2x and it outputs, let's say, a very low output. I want to say that this satisfies G of X and X prime equal to 0. Then our guess is that any algorithm that succeeds in finding such pair must query G so many points to find this pair. Because G and H are independent. If you take one collision from H and you query this collision pair on G, you will very likely to get a non-zero string rather than a zero string. So this means that if you get a zero string, you must query G on so many points. Now, if you look at the compressed oracle database of G, what you get is a compressed database that consists of many collision pairs in H. So this goes, the compressed Oracle database serves as the write-only tape in the original long output problem. So this means that we are able to still apply this slicing technique in a setting where we don't really have a long output problem, but in this problem, we have an intermediate layer, this G, like the database of G, that gives you like an interface between a short output problem and a long output problem. Okay, so this page is the most important takeaway I want you guys to have. So, are there any questions on this? Okay, so let's continue.
Sorry, so the output tape is the write-only tape is the same as the output tape, or no? Write-only, no.
Yeah, I mean, so here there are some subtleties here, but I mean the idea is that in the original long output problem, you have a physical output tape. But here in this new problem, you don't have this output tape, but what you have is a Oracle G. This G serves as a output tape because previously in this slide, we know that a Oracle itself is a write-only tape. If you look at its compressed Oracle database, or if you are not familiar with quantum, I can use a classical analog for this. It's like if you look inside the lazy sampling procedure of an Oracle, you would actually notice point by point queried by the algorithm. And if you record all of these points, you get a stream of output. So here, this G will receive multiple queries from the algorithm because the algorithm is the goal of the algorithm is to find a G of x and x prime equals to 0. So it must be querying G for so many times. And if you look at this query process, you'd actually record so many pairs such that they form a collision in with respect to H. And this will serve as the serve as the write-only tape. It will record the output of the problem.
Right. So normally the way the compressed Oracle is used is that, like if you're making poly-many queries, then you argue that somehow the simulation is efficient, and then you should be able to extract collisions from the database and so on. Here you're saying that if it's a long output thing, then because I can simulate the random Oracle essentially using a very long output tape, this long output tape would contain collisions. Is that
yes.
the right way to think about?
Yes, partially correct. I mean, actually, it's like the other. The logic is it's like the other way around. Like you have this Oracle, and this Oracle, if you take the compressed Oracle view, then you are doing the exact same thing as this long as what is done in the long output problem. Because in the long output problem, you are kind of like XORing your answer on the output register. Here you are XORing your quantum queries to the compressed Oracle database. So it's essentially the same thing.
Okay, thank you.
Okay. Yeah. I mean, actually, there are some subtleties here. I will explain this by the end of the talk. Like these two are not exactly equivalent, and there's a big issue here. But for now, you can think of it as a perfect simulation. So,
can I ask a question?
Yeah.
So, in the reduction, are you always reduced to this k distinct collision problem, or actually some maybe also other problem that have large output space?
Actually, we're actually using other problems because using multiple collisions problem, there's a barrier because we cannot prove like a real space-time trade-off if we use that problem. Like the bound is not good. It's not because that it is not a space-time trade-off, but it's because we are not we don't have a good tool to prove a valid space-time trade-off. The bound is not good, so we actually use some other problems that are similar to this K collision finding problem.
Got it. Okay, thank you.
Okay. And okay, so our result is the following. So there exists a problem called this nested collision finding. You'll get what this means in the next page. Under the quantum random oracle model, such that we have a lower bound, which is that, we have an upper bound that there exists an algorithm with S and T equals to n to the 1/3, where n is the size of the image. And for lower bound, we have that for any algorithm with limited quantum memory, it requires n to the 0.35 number of queries. So this is like a space-time trade-off. Also, we have a similar result for the classical case, but for the classical case, it's not 1/3 and 0.35 is some other real number, but it's like it's the same type of result.
So you're given access to a random oracle which goes from n bits to n bits, and you have to recursively compute it and find a collision. Is that the problem?
No, actually, you have multiple oracles. But anyway, like multiple oracles is equal to the same oracle because you can like merge oracles with you can expand the domain. Yeah. So it's something like that, but you have like two independent oracle, and like here you have H and G. The nested words means you have two oracles, one in the other. Like you have to first find a collision type of thing in the first oracle, and this pair actually satisfy another constraint in the second oracle. So it's called like a nested collision finding. Yeah.
But this is relative to a random oracle, or the separation, or is the structure in the problem?
This is in the quantum random oracle model. I wrote here. It's in the quantum random oracle model.
Sorry.
Yeah. I mean, if this is in the plane model, then it would be a very, very interesting result. I mean, plane model space lower bound are notoriously hard. Yeah. So.
No, I thought the oracles are somehow structured. I was asking for. I thought it's a weaker result.
Oh, it's not. It's not structured. Yeah, it's a random oracle model. Yes. So an application of this result is the following. So we actually have a message that shows quantum speed up needs space. This message is decomposed into the following two lemmas. Following two property on a oracle search problem. So there exists an oracle search problem such that with limited memory, classical algorithm is as fast as the quantum algorithm, like optimal complexity. But with unlimited memory, quantum algorithms outperforms classical algorithm. So the way of constructing such a problem is very easy. It is even a black box way. So let's write down some points on the space-time diagram. These two red points are classical algorithms for nested collision finding. So with limited memory, the classical algorithm is worse than the classical algorithm with unlimited memory. And these two blue points are for quantum algorithms. Then we want to construct this problem we want that we want is to satisfy speed up needs space. This problem is called solve A or solve nested collision finding. So what is A? A is like a dummy question. Like these two yellow points are the best algorithm for A. A is like you guys can think of it as like a dummy question, like for example, answer the sum of all oracle outputs or something, which the query complexity of A does not depend on the size of the memory or whether you are quantum or not. It's like a very bad question. And this question has complexity between these two blue lines. So Now let's analyze what is the complexity of solving this new problem, like this new OR problem, solving A or solving nested collision finding. If the memory is limited, then both classical and quantum algorithm will choose to solve A. Because for this line, the optimal complexity is to just solve this this dummy test. If the memory is unlimited, so if the memory is limited, we get a classical algorithm as fast as quantum algorithm because they both want to solve A. If the memory is unlimited, then, well, the classical algorithm will try to solve A, but the quantum algorithm will try to solve nested collision finding. So here we get a quantum advantage. Yeah, I mean, this construction is really, it sounds like dumb, but yeah, so here's the message. Yeah, so now let's go back to the nested collision finding. So we're here to formally define this problem. So we have two random oracle H and G. H is a random oracle from M to N, where this, well, you can think of M as polynomial, poly N, like it's a large domain. It's a large enough polynomial. And G is an oracle from M to the L to N0, like there are two random oracles. And the task is to find two distinct pair. Here, by saying distinct, I mean these two tuples, ordered tuples, are distinct. Not all the elements are distinct. It's the tuple are distinct, such that both of their sum in H, like this, this is I will call it sum later for all of this talk. The sum of H of xi equals to the sum of H of xi prime are equal to 0. Like we are having this model here. Like you guys can think of this like a f n, or it's like a field you can add, or you can add in this field. They are equal, like the sum of these two tuples under H are 0. And there's an additional constraint that says these two pairs form a collision in G. So this is why we name this problem as nested collision finding. So it's basically like a collision on top of collision. So the restriction on the tuples is just the normal restriction. Like we wanted this tuple to be there's an order, like permuting a tuple does not count as a new one. And today we will focus on the case where n0 is equal to n and l equal to 4. So actually we have, like, for many parameter regime, we can get the space-time trade-off, but this is like a one example. And also, let me just say that there is an algorithm. Like we will not prove upper bound in this talk because it's like a Grover search on top of Grover search stuff. We'll just say that there is this algorithm that solves this question with n to the 1/3 queries and to the 1/3 space when this under this parameter regime. So once you understand the two-oracle recording technique, basically you know how to solve, how to prove this, how to prove lower bound for this problem. Proof is essentially, let's say now you have an algorithm that finds these two tuples, and this algorithm will interact with both random oracle. It will, this red part is it's its interaction with H, and this blue part is its interaction with G. And the reduction is very simple. You just look at its communication with G, and you simulate this G using your compressed oracle. And in the classical case, it's just lazy sampling. In the quantum case, it's simulating it with a compressed oracle. And you rate out some number of tuples with sum 0 in H. Because the algorithm is trying to find it's trying to find collisions in G. It must have queried so many points on G, so that you can read out all of these points such that it has some 0 in H under H. Then this reduction will give you an algorithm that solves the massive output problem, or like the long output problem, where this long output problem is like find out k tuples of some 0 under H. So formally, the reduction says that let's say you have an algorithm that queries both H and G at most t times.
So before you start with the formal thing, I had a small question, which was that is there like some intuition for why taking the sum of the hash under H to be 0 is the right object to consider?
Well, actually, you can consider so many problems in the inner, like there are 2 layers. In the inner layer, you have this problem on H. You can actually consider so many problems, but this is just for an example. Yeah, yeah, maybe you can consider like a collision, multiple collision thing, or like, I mean, this is like only an example here.
Property
it's well, I mean, it's easy to analyze because the form is good, but I believe that you can come up with some other problems in the inner layer. I mean, I mean, this is not the most important part in this result, because like essentially the whole thing, the most important part is to use random oracle as a write-only output, a write-only tape. Yeah.
Okay, thank you.
Okay, so the formal proof is to, let's say you have an algorithm that queries both H and G with at most t queries, and this algorithm wins if it only it finds this valid tuple pair. So this lemma here, we can prove that if, let's say, if the expected database size, so here expected database size is like a sample a random time, and at that time you measure the database, and you count the number of non-bought entries in the database. If the expected database size of G is, let's see, V, then the probability of the algorithm outputting this collision of G, like because this pair is a collision under G. So if the algorithm succeeds in this, if the algorithm has a expected database size V, then its success probability is bounded by VT divided by N. I think there should be a big O notation, but yeah, just ignore it. Oh, sorry, wait. No, there's no big O notation because here is the I mean, anyway, you can think of a big O notation here. It's like an order. This is the order of the probability. Yeah, I'll add it here. Like the order of the success probability of this algorithm is VT divided by N. And so this means that if you view this reduction in the database, if you view this game in the database view, then what you get is this. So still you have this algorithm with a similar constraint. Now, let's say you measure the database of G, and you only care about positions where it forms a zero-sum tuple under H. The algorithm wins if the number of such positions is at least n divided by t. So these two are connected by this lemma. So here, this second database view is somewhat similar to what we have before, like a long output problem. Okay, so it's basically you want to find n divided by t number of tuples, sum up to 0 under H. Yeah. And if we, on the other hand, besides this, we can prove a time-space trade-off for finding k tuples of sum 0 under random oracle H. Then we can combine these two results to say that for this short output problem, there's a space-time trade-off. Okay. So here is like basically the formal reduction. So this space-time trade-off for finding k tuples, we have discussed this before. It can be separated into two steps. The first step is to find a probability bound. By saying probability bound, I mean a relation between the probability that you can find. The probability bound is like the probability you can find k tuples with t queries. What is the probability of this? And combine this with the slicing technique, you get the space-time trade-off. Well, actually, there are some really subtle things here. So I mentioned several hardness in this proof. The first technical challenge is this problem. So it's here, it's this one. So now let's say that you want to get a probability bound on finding k tuples in t queries. You might notice that there is actually a difference between this and the k collision problem. In the k collision problem, we said that it's a bound for finding k distinct collision, where this distinct acts on like all the inputs. Like for all these collision pairs, they are distinct on their inputs. Here, we don't really require this to be distinct. So this is to say that you can have two tuples intersecting on its elements, like they have intersections on of their elements. So this makes the proof much more harder. Previously, we only know this type of argument. We only know that the probability bound for finding k tuples of distinct elements with t queries. So now we want to prove this. So how do we prove this? Well, it's a similar argument, but let's analyze why it fails here. So let's say that we are doing the same thing. We are trying to do the progress measure. Let pi k be the projector onto the database such that the database contains k tuples of sum 0. And let this delta tk be the amplitude of the state. So what should be this question mark? Like, what is the coefficient here? So actually, well, you might notice that with one query, like each time when you query a new element, the number of new k tuples generated is not at most 1. You can have like there might be the case that after you add this element, you get, let's say, 10 tuples of sum 0 rather than 1, because here you are not requiring the tuples to be distinct. So we don't really have a recursion. What we have is something like this. We have a summation over different j's, and where we have this coefficient a t minus 1j means that the probability that the new entry forms j zero-sum tuples with previous non-bound entries. So this actually causes you a problem. Like if you bound this like this, then you get a really bad bound. You don't really get a bound that is suitable for later proofs. So can we optimize it? So now we'll mention the correct proof. So we're actually doing inductions for L, because here L is like a, well, we can think of L as a constant, so we can do induction on L. If L equals to 1, then this tuple collapses to a single element. This is easy because we know that we can easily bound the probability of finding k pre-image of zeros, right? Then for a larger L, if the algorithm wants to find k L tuples of some y, here is not some zero. Because of induction, later you will know where here's a y. So for any y, if you want to find k tuples of with some y, then this algorithm either has this property. So at some point, this algorithm must contain at least L. Sorry, I used the same letter, but like L smaller tuples with the same sum, or the number of interesting query is at least k divided by L. So interesting query here actually means that after this query, the number of L tuples of some y increases. So it's like a pigeonhole principle. So either you increase k divided by L times, or at some point there are more than capital L smaller tuples in the database, so that it guarantees you the possibility that for one step you can get more than capital L number of L tuples of some y. So to draw a graph, it's like this is the number of tuples. And this is t. It increases like this, right? So if this is k, then either you have k divided by L jumps, or you have one interesting jump. Let's say here, this is larger than L. So how do we make this larger than L? If you want to add a new element and you add larger than, like more than L tuples of some y, you must have at least L capital L smaller tuples, which can form, like by adding a new element to the smaller tuple, it can form a large tuple of your desired sum. So this is like also a pigeonhole principle. So for this part, for this first part, we know it because we are in an induction. So this part, like the first part, is basically from the result where, like from induction, we have this L minus 1 tuple. Actually, it should be like L minus 1 tuple. Yeah. So after this, like the second part is standard Oracle recording techniques, because now you are not counting the number of tuples, you are only counting the number of interesting queries. And combining these two parts, and also apply a union bound over all y, you get a statement like find k L tuples with the same sum. So this would give you the lemma, would give you the result that you want to use in the next layer of the induction. So combining these two, we solve this challenge. Yeah, before I present in the second challenge, any question for this one? Okay. So the second challenge is what I want to mention. What I mentioned before when we share the Oracle duality page. So basically, the second challenge is to say that it is not exactly the same thing. Like this write-only tape and Oracle database is not exactly the same thing. So consider the following question. So in the slicing technique, we want to merge two slices. into one. And basically the way we merge is like a union bound. Like in the classical case, we use union bound. Like you have 2 slices. Each of them, let's say, each of them are able to output k divided by L tuples with T divided by L queries. And the probability that there are it answers more than k divided by L tuple is very small, let's say epsilon. So if we merge these two slides, do we actually get an algorithm that outputs that write at most 2 times k divided by L tuple, except with probability polynomial of epsilon? So this is actually true in the classical case, because in the classical case we have union bound. Like if it wants to output more than 2 times k divided by L tuples, it must, like this exceeding tuple must come from either the first part or the second part. We have this pigeonhole principle. We can use union bound, and this is also true in previous quantum long output problem paper, because previously their model, like in their model, this write-only tape is like a real write-only tape. Like once you write something on the tape, the tape is instantly measured and you get the classical result. So here, in our case, because we are using a random oracle, it's not the case. Like intuition why this is not the case is that in the random oracle, you can actually erase your output. Like you are using a C0 gate to access the random oracle, but we know that quantum C0 is not a write. It is essentially creating entanglements, and you can undo this process. It's not like exactly write. So now let's consider a very simple problem. This will capture the idea of this technical challenge. So let's say there are 2 quantum algorithms. They share a common output register D. They are allowed to use C0 to modify D. So basically, it means that you can apply a C0 where the target is on D, and the source, like the control, is on the algorithm. So you have A that only operates on A and D, and they only modify D with C0. And you also have B. B can only modify D by C0, and A and B are not, they does not share any common memory besides D. Let's say if we run A or B, we will run one of them, then the probability that there are k bits flipped on D is epsilon A or epsilon B, respectively. Like if you only run A, then there with probability epsilon A, there are more than k bits flipped on D. If we run them together, in the classical case, if we run them together, then we obviously get the union bound type of result. Like the probability that there are more than 2k bits flipped on D is at most epsilon A plus epsilon B. Quantumly, one would suspect that the bound would be something like square root epsilon A plus square root epsilon B squared. Like the idea of this is like adding amplitudes up. But this is not true, actually. And we have a counterexample. By the way, a funny thing of this is that we didn't really wrote this counterexample in the paper. By the time we submit this paper, we don't know whether there's a counterexample of this. We just know we just don't know how to prove or disprove it. And this counterexample is found by GPT 5.6. So to actually resolve this problem, we need a very, very complex argument from a paper previously by Qipeng. And the idea is that, well, this tail bound is not true, but the expectation version is true. So now if you switch the tail bound into expectation, let's say if you run A, then the expected number of bits flipped is Ka. If you run B, then the expected number of flips is Kb. Then if you run them together, well, you get the good result. you get the good union bound type of result. So expectation is good, but to convert this tail bound into expectation with a advice is very hard, because if you naturally convert this, if you naturally guess advice, you will get a boost on every position. Like expectation is taking some, like it's a sum of probability of every bit flipped. But if you guess the advice, like the probability on every bit flips will be boosted by 2 to the s, which will give you a useless bound. Yeah. So I will not mention the techniques so that do this convert. This is really not relevant to the main message of this paper, but it's a very interesting technique. If you're interested, just look at the paper. So the main takeaway of this paper is that we actually construct a strong time-space trade-off for short output problem in the random oracle model, both in the quantum and classical setting. And this new technique of oracle recording, like 2 oracle recording, is very useful in terms of doing this reduction. When operating with when we try to prove something with a quantum random oracle, especially for space for progress measure type of problem, you should always think about this quantum duality. Like quantum algorithm itself is a right-only register. So yeah, this is the main takeaways, and yeah, that's all of my talk. Any questions?